Hello everyone, I'm Yongsheng. I'm giving the presentation of our paper MPD, Moving Target Defense Through the Communication Protocol Dialects. With the development of the Internet of Things, its scale is increasing. The Internet of Things has diversified capabilities, such as sensing, actuating, processing, and communication. IoT integrates into various enabling components like software, application libraries, middleware, embedded system, and network artifacts. Any vulnerabilities in these components will lead to exploitations to create the service attack. So IoT-related vulnerabilities are common, like the denial of service attack and the reconnaissance attack. Therefore, a dynamic defense method is needed. Recently, we raised up the moving target defense idea. The moving target defense MPD will diversify the attack surfaces and randomly change the properties of a target configuration. This consistently evolving defense will decrease the attack efficiency, such as we can change the IP addresses and the port numbers to realize the random port and the address hopping. So the motivation of our MPD design is that regular MPD method has limitations, because the configurations of a lower level attributes such as the IP addresses and port numbers restricted the defense diversity. And many low and IoT products do not have the strong security mechanism embedded. This will lead to a security threat in the IoT protocol. Apart from that, customizing a standard protocol can create more variations. We will leverage application layer properties and select a customized protocol with MTD dynamically to stop the attack from happening. We give some threat models in the IoT protocols. The first one is the denial of the service attack. This attack existed in the Message Queuing Telemetry Transport Protocol, which is MQTT. MQTT is a lightweight publish-subscribe network protocol that transports the message between the devices. Assuming we have the attacker client that try to flood the server with the malicious connect request. Because the server cannot tell the difference between the malicious connect request and the legitimate connect request. Assuming that the server receive a lot of connect requests at the same time, its buffer will drain out. So if we have a legitimate MQTT client that try to send a connect request to the server, the legitimate request cannot get through because the buffer has already been drained out. The second type of attack is the inject command attack. This attack existed in the controller area network CAN protocol. The CAN protocol is a message-based protocol designed to allow the microcontrollers and devices to communicate with each other applications. So we have a attacker electronic control unit ECU here. So the attacker ECU will send the malformed packet into the CAN bus, and this packet will distract other ECUs and force them to execute the malformed actions, therefore to crash the system. So our MPD method aims to customize a standard protocol and create moving target defense by fabricating the desired protocol dialects and allowing servers and clients to dynamically select the dialect in a synchronous way. We give the definition of the protocol dialects here. Give a standard communication protocol. A dialect is a variation created by mutating its packets and handshakes while keeping the communication functionalities unchanged. We design our system in 3 modules, which is the moving target customization, self-synchronizing mechanism, and the protocol dialect management. The MTC module will focus on creating customized packets using dialect generating functions, and the SSM module ensures the server and the client remain synchronized with respect to their selected dialect. At last, the PDM module selects a protocol dialect for the packet. So the figure here tells us the relation between all these modules. So we have a sender and a receiver and a communication channel. Follow the blue arrow that the original packet will be passed into the MTC module in sender, and the dialect generating function will apply a dialect in this original packet. And this customized packet will send through the channel to the receiver, and the receiver will use the inverse function in the MTC module to recover the original data. Follow the green arrow. The packet will be cached in both in local buffer on both sides, and then feed this cached packet into the SSM module to generate the pseudo-random number. And following the red arrow, this pseudo-random number will be fed into the PDM module to calculate the dialect index n for the last packet. And also, this pseudo-random number plays a very important role in keeping self-synchronization of both sides. So we introduce the moving target customization module first. The MTC module utilizes the dialect generating function to create the protocol dialects. The function can sufficiently mutate the communication packets, and the inverse function will recover the original packets. So we have two examples to customize the dialect. The first one is the shuffling function, another one is the splitting function. The shuffling focuses on generating various protocols dialects by switching randomly selected segments from the original packet in application layer. And the splitting will generate the dialects by splitting the application layer information of one packet into several sub-packets. So here is the first example of shuffling. We define a packet M of length k bytes, and three parameters is the first is P is the starting position of one segment, and O is the offset between two starting positions of a segment, and L is the length of the two segments. So the combination of the P, L, and O is mapped to the dialect index. So the dialect generating function D to create a custom packet of M prime is defined like this. And also we have the inverse function to retrieve the original data back. So we use the graph here to further illustrate this idea. We have the packet and we grab two segments, S1 and S2. So the S1 is ranged from P to P plus L, and the S2 is ranged from P plus O to P plus O plus L. So the shuffling function will shuffle these two segments. So the S2 will be the position of the S1, and the S1 will be the position of the S2. Then we get the customized packet M prime. The second example is a splitting function. So the splitting is try to split one single packet M of k bytes into 4 subpackets. We define the subpacket number of 4 here, with length of the T1, T2, and T3 of the first 3 subpackets. So the combination of the T1, T2, and T3 is mapped to the dialect index n. We have the dialect generating function D like this, and correspondingly we have its inverse function. The graph here is trying to illustrate this idea. So we have the original packet M, and we split that into the subpacket Mi prime. So the Mi prime have a different length defined by the T1, T2, T3, and the K minus the summation of the T1, T2, and T3. After that, we send this subpacket to the receiver, and receiver will merge this again to retrieve the original packet back. The second module is self-synchronization mechanism, SSM. The SSM module ensures the unpredictability and the synchronization of the dialect selection. The client and server select the dialects unpredictable to eavesdroppers, and the dialects on both sides remain synchronized during the communication. So this is the functionality of this module. The SSM will leverage the pseudo-random number generator to create a randomness for selecting random dialects. The function we use for the pseudo-random number generator PRNG is the k-hashed function. So the input of this function is the previously cached packet Mi-1, and this packet is cached in the local buffer. As the equation shows here, that the hash function h can be selected, such as the MD5, and the secret k in this equation is pre-shared between the client and the server. We use a figure here to further illustrate this idea. So we have the both sender and the receiver, and we assume that the packet 2 is missing during the communication. Because for sender, it will assume that the packet 2 is successfully sent, so it will update its buffer with packet 2. However, for the receiver, because nothing is received, so the content in the buffer still be the packet 1. That means for packet 3, the contents in the buffer are different. So for both sides, it will generate a different dialect index for the packet 3. So the packet 3 cannot be synchronized. However, this error will only be propagated for one cycle. After that, both sides will store the packet 3 into their buffer. So for the packet 4, it will back to synchronize data again. The third module here is the Protocol Dialect Management, PDM. PDM module allows easy operations of the protocol dialect in the framework. So the operation includes adding, deleting, or replacing a protocol dialect, and the PDM module selects a dialect for the coming packets. Referring to the consistent hashing and the key-space partitioning, we design the consistent hashing to map the pseudo-random number to protocol dialect index n. Assuming the distance among every two indexes is equally distributed, we can calculate a certain dialect index n given the pseudo-random number s from the SSM module. The equation present here. If we add or delete a dialect, we have to update the total protocol dialect number and max. We give a figure here to further illustrate our design of consistent hashing mapping. This scenario is about adding a new dialect. The circle here represents for the pseudo-random number ranging from 0 to its maximum when traveling clockwise, and the points on the circle represent for different dialects. The distance between 2 points is delta, counting by traveling clockwise around the circle from the dialect index n to n+1. So if we assume there is a pseudo-random number located here on the circle, so it will be assigned to the dialect number 2. If we add a new dialect in the system, there will be 5 points on the circle, so the distance between 2 points will be shortened to dialect prime, which is the 1/5 of the circle. And the same pseudo-random number on the circle will be assigned to the dialect 3 in this graph. The setup for our evaluation is listed below. The system we are using is Ubuntu 18.04 LTS with 16 GB memory. The target protocols is FTP and MPD. So first we test the MTC module. The first one is the shuffling function. We're computing for the different FTP get command. As we can see in this table, that for different dialect index, the combination of 3 parameters, position, length, and offsets are different. So we are using different dialect to customize the original packet into the customized ones. And also we repeat the same process for the splitting function. And still we're computing for different FTP get command. And we can see we use a different dialect index with different combination of the parameters, and we customize the original packet into different customized subpackets. And also we try to illustrate our self-synchronization by giving the experiment to show that our method can help to define the packet erased or missing. So we set the packet 1 is erased or missing during the experiment. So we can see for the iteration 1 that the cached packet is the packet P, which is the previously sent packet. So both sides is synchronized. However, for server, there is nothing received. And for the iteration 2, as we can see that because the cached packet on the client and the server are different, so the packet 2 can't be synchronized. However, for the start from the iteration 3, that the cache packet will remain synchronized again, so the system will back to self-synchronization status. Next, we do experiment to prove that our method can help to defend the DOS attack. This experiment is based on the MQTT. So the attacker MQTT client will try to flush the modified MQTT server to exploit its buffer by continuously sending the connect packet. As we can see, this attack is failed because the attacker MQTT connect request cannot pass the dialects index check on the modified MQTT server. In the last, we test the overhead of our modified FTP implementation and compare that with standard FTP implementation. We test this on the server side and we run each experiment 4 times and record the average overhead. We execute 1 billion FTP get command to retrieve a small text file from the server. As we can see in this table that our modified FTP with MPD embedded only has a small overhead increasing compared to the original FTP implementation. The elapsed time, which is the time we spent to execute the modified FTP program in the kernel, only increased a little bit, and the maximum resident set size, which is the memory space we need to use to execute the MPD program, is correspondingly increased a very small scale. In conclusion, we design and evaluate a log moving target defense framework, MPD, which generates the sufficient customized protocol dialects. MPD can dynamically select dialects in a self-synchronous manner, and the experiment results using the FTP and MQTT indicates that MPD can harden the security while incurring a low execution overhead. In the future, we will integrate the MPD into other protocols and also explore different pseudo-random number generators in our design. That's pretty much for today's presentation. Thank you for listening.